Hi all. So in this small video, I'll be discussing about Coulomb gauge. Okay, we have already said that in case of the potential formulation, we always have a freedom to choose our potential. So from one set of potential V and A, we can always transform to some new potential V prime and A prime, which gives the same field. So we can find the new potential by imposing some new condition according to our convenience. So this kind of freedom is called gauge freedom. Okay, gauge freedom and corresponding transformation is called the gauge transformation. So this both V and A will give the same field. Okay. Now, what is meant by Coulomb gauge? So this is one way of choosing the potential. So in Coulomb gauge, we'll choose the vector potential such that del dot A would be always 0. So will choose the A. We will choose a vector potential in such a way that del dot A would be always 0. So this condition is called the Coulomb gauge condition, or this condition itself is called the Coulomb gauge. So we always have a choice on the potentials. So we can choose the potential as we want. So in case of Coulomb gauge, we'll choose the vector potential in such a way that del dot A equal to 0. So correspondingly, the scalar potential will change. So that we are not going to bother now. Okay, the scalar potential will become more complicated, but the vector potential now becomes simple. Vector potential is taken to be solenoidal. That its divergence is 0. So if its divergence is 0, then what will happen to the first equation? If del dot A equal to 0, then in Coulomb gauge, what we'll get is we'll get del square V equal minus rho by epsilon. That means we'll get back our the original equation called the Poisson's equation in electrodynamics. So this equation is called the Poisson's equation. So if you set del dot A equal to 0, we'll get the Poisson's equation. So the computation of scalar potential would become very easy now in Coulomb gauge. So this is nothing but the Poisson's equation. So therefore, the computation of V will be similar. Okay, so that means what would be the potentials? The potential V, we can always write 1 by 4 pi epsilon 0 integral rho of r prime d top prime modulus of r minus r prime. So this we can do. Okay, so this would be the potential at r. So this is a solution for del square V equal to minus rho by epsilon 0. So the potential computation now become very easy if you use Coulomb gauge, but whereas the computation of vector potential has to satisfy this particular equation. Now that would be more complicated. Okay, so that is we have to tell about the Coulomb gauge. So in Coulomb gauge, the condition is del dot A 0, and if you set del dot A 0, the potential the differential equation satisfied the potential, the scalar potential would become similar. It will take the form of Poisson's equation, and its solution is very straightforward. But whereas the computation of A would be difficult. Okay, so that also we can write. But computation of A would be difficult. So that would not be any straightforward because the A has to satisfy this lengthy equation. So that would be difficult. So that's about the Coulomb gauge. So next we can discuss about the Lorentz gauge. So in the Lorentz gauge, we have the same set of, we can start with our original differential equation. Okay, so these are the differential equations we have, the Maxwell's equation potential formulation. So in Lorentz gauge, the additional condition that we'll do is we'll set this term as 0. That is what we are going to do. Okay, so in Lorentz gauge, we'll set del dot A plus mu 0 epsilon 0 dou V by dou T equal to 0, or del dot A become minus mu 0 epsilon 0 dou V by dou T. So this condition is called the Lorentz gauge condition. So if that is the case, what would be our Maxwell's equation? What would be its transformation? So we can check it here. So del square V plus dou by dou T of del dot A is 0. So that become del square V, and dou by dou T of del dot A. Del dot A is this. So this become minus mu 0 epsilon 0 dou square V by dou T square equal minus rho by epsilon 0. And what about the second equation? The second equation takes the form del square A minus mu 0 epsilon 0 dou square A by dou T square equal to minus mu 0 J. Okay, so now if you look at the Maxwell's equation in Lorentz gauge, so this is in Lorentz gauge. So the both the scalar potential and the vector potential has the same mathematical structure. So the left side seems to be a wave equation. So this is it seems to be a wave equation with a source term, and the vector A equation also a kind of wave equation with a source term. So we'll get a inhomogeneous wave equation. So the thing is, the importance is in case of Lorentz gauge, both V and A has equal importance, and it obeys equation of same mathematical structure. So it has same mathematical structure. So we can combine these two and we can simplify the equation. So they use a new expression called D'Alembert del square. So which is defined to be del square minus mu 0 epsilon 0 dou square by dou T square. So hence our in Lorentz gauge, the scalar potential will satisfy the equation D'Alembert V equal minus rho by epsilon 0 and D'Alembert A equal minus mu 0 J. So this symbol, this square, is called D'Alembert. It's called D'Alembert. So D'Alembert symbol is square. So okay, so that becomes the beauty, the structure. Now this mathematical equation has structurally it becomes very simple and very clear. Now what about in the source-free region? So in the source-free region, the rho and j would be 0. Okay, so with that we will finish the discussion. So in the source-free region, rho is 0 and j would be 0. And what we'll get is del square v minus or del square v equal mu 0 epsilon 0 dou square v by dou t square, and del square a gives mu 0 epsilon 0 dou square a by dou t square. So this is nothing but a 3D wave equation. So in Lorentz gauge, the equation satisfied by the scalar potential and vector potential now seems to be symbol. So in the source free region, it obeys the three-dimensional wave equation, and in the source region, it still obeys three-dimensional wave equation with the source term. Okay, so in the Lorentz gauge, the both potential, the scalar potential and vector potential is coming in the same footing. It take the same structure, the same mathematical structure. So that's why we call it gives us equal importance for both the scalar potential and vector potential. And the source free region, the scalar potential and vector potential satisfies a simple differential equation called the wave equation or three-dimensional wave equation. So that's all about the gauge freedom and the two different gauges we have discussed, the Lorentz gauge and Coulomb gauge. In Coulomb gauge, why the term Coulomb comes, the reason is in Coulomb gauge, which set del dot A equal to 0, we set del dot A equal to 0, that gives the scalar potential obeys the Poisson's equation, and which is directly derived from the Coulomb's law. Okay, so that is why the term the Coulomb gauge, which is come over here. So the computation of V would be similar, but the computation of A, it would not be simple. The A would become complicated. So in the Coulomb gauge, the V and A are not in equal footing. The structure of equations satisfied by the V and A are entirely different. So whereas in the Lorentz gauge, both V and A have the same mathematical structure. And what is a Lorentz gauge? So the question is what is Lorentz gauge? The Lorentz gauge condition is del dot A plus mu 0 epsilon 0 dou V by dot equal to 0. Okay. So if you cannot recall it, better write the Maxwell's equation in terms of scalar potential and set this bracket at 0. That is the condition of Lorentz gauge. Okay, so thanks for watching this video. So with this, we have completed the discussion of the electrodynamics chapter. And the next remaining chapter, the last chapter, would be the discussion about the electromagnetic waves. So that we will start in the next class onwards. So thank you.